Right now, at the very boundary of our solar system, there exists a world shrouded in a blue atmospheric veil woven from toxic organic compounds. A world whose surface is blanketed in nitrogen ice so impossibly cold that the atmosphere above it can solidify and fall to the ground like snow. A world where the light of a sun positioned 40 times farther away than the one that warms your skin barely penetrates the surface at all. For generations, humanity dismissed this world as a harmless cosmic curiosity, a small, frozen punchline stripped of its planetary title and exiled to the footnotes of astronomy textbooks. Then, the James Webb Space Telescope turned its instruments toward Pluto for the first time, and what it found dismantled the comfortable image completely. What Webb uncovered was not one single terrifying secret. It was something considerably worse. Pluto is alive in ways that make the outer reaches of our solar system feel darker, colder, and far more inhospitable than anyone had allowed themselves to imagine. If you find value in journeys that permanently alter how you understand the universe around you, I would genuinely appreciate it if you took a moment to hit that like button and subscribe. It costs you nothing, and it means everything to this channel. We are also now available on Spotify, and the link is waiting for you in the description if you prefer to listen on the go. Now, find somewhere comfortable. Let's begin. Everybody loves Pluto. That is precisely the problem. For the better part of a century, human beings have treated this remote frozen world as a kind of cosmic mascot, a sentimental underdog, a small, pale wanderer that astronomers bullied when they stripped away its planetary classification and reassigned it to the back pages of the solar system catalogue. People responded with genuine emotional investment. They wore t-shirts. They placed bumper stickers on their cars. When NASA published the first detailed close-range photographs in 2015, millions of people fell in love with a heart-shaped expanse of nitrogen ice and decided, collectively, that Pluto was endearing, and that emotional imprint is still the one most people carry today. A modest, harmless snowball drifting in quiet solitude through the outer dark. Something between a forgotten toy and a gentle mascot. The ninth planet that was no longer a planet. The misfit that the scientific community voted out of the club. People feel a protective instinct toward Pluto. They feel a kind of nostalgic tenderness about it. They project human emotional states onto a body composed of rock and frozen gas that orbits so far from the sun that midday on its surface is dimmer than a heavily overcast afternoon on Earth. This sentimental attachment is not merely a harmless quirk of popular science culture. It has constructed a mental image of Pluto that is almost entirely disconnected from physical reality. The misunderstanding is not simply a matter of getting individual facts wrong, though that happens too. The deeper problem is that the entire emotional framework people apply to Pluto is a fiction. The real Pluto is not endearing, it is not quaint, it is not a peaceful little outcast drifting gently through the void. The real Pluto is among the strangest, most chemically aggressive, most climatologically extreme environments in our entire solar system. A place where the atmosphere itself may be actively freezing and collapsing downward onto the ground. Where complex organic poisons drift through a blue haze that extends hundreds of kilometers into a sky that is functionally indistinguishable from deep space. Where the light arriving from a distant sun delivers so little thermal energy that the difference between the warmest and coldest points on the surface spans a range that no human being has ever experienced in any context, in any climate, on any part of this Earth. None of this is visible in the popular image. The popular image was assembled from decades of observational distance, emotional projection, and a small collection of spectacular but fundamentally incomplete photographs. And it has taken the most capable space observatory ever placed in orbit to finally pull that image apart. When we describe the James Webb Space Telescope's examination of Pluto as a first, that description requires precision. This is not the first time humans have observed Pluto. We have known of its existence for nearly a century. We have photographed it. We have flown a spacecraft past it at close range and returned images of extraordinary detail. What Webb did was something categorically different. It observed Pluto in a range of wavelengths that no previous instrument had ever been able to access from this distance, and in doing so, it revealed physical processes that had been completely invisible to every observation that came before. Not because those earlier observations were poorly designed, but because the processes themselves only become visible when you look in the right part of the spectrum, and no instrument before Webb was capable of looking there with sufficient sensitivity and resolution. To understand why this matters so profoundly, you need to understand what the popular image of Pluto is built on and how systematically that image has been assembled from incomplete information that left the most important questions entirely unanswered. The comfortable version of Pluto is a product of distance. When an object is so far away and so faint that the best available instruments can render it only as a smudge or a point of light, human imagination fills the gap. The imagination, being a human instrument, fills the gap with human things, with warmth, with meaning, with emotional associations that have no basis in the physical reality of the object being imagined. Pluto was small, so it became an underdog. It was far away, so it became a symbol of loneliness. It was stripped of a title it had held for 76 years, so it became a figure of cosmic injustice. None of these are properties of Pluto. They are properties of the human mind encountering a subject about which it has almost no actual information and doing what human minds have always done in the presence of uncertainty, projecting inward rather than observing outward. The James Webb Space Telescope does not project, it measures. And what its measurements reveal about Pluto is a world so physically extreme, so chemically active, so climatologically alien, that the gap between the sentimental image and the scientific reality becomes, once you see it clearly, almost impossible to bridge. That gap did not open suddenly with Webb's observations. It has been widening for decades, with every incremental improvement in our ability to see this world as it actually is rather than as we imagined it to be. Each step forward in observational capability has made Pluto less familiar, not more. Each new instrument, each new measurement, each new data set has pushed the dwarf planet further from the comfortable mental category in which most people have filed it, and deeper into a category of physical reality that is colder, stranger, and harder to sit with than anyone expected. Webb did not begin this process, but it may represent the moment at which the process crossed a threshold, the moment at which the accumulation of physical detail became dense enough that the sentimental image can no longer coexist with the scientific one, the moment at which Pluto stopped being what people wanted it to be and became, unmistakably and irreversibly, what it actually is. And what it actually is, seen clearly, in the mid-infrared wavelengths where its thermal behavior finally becomes visible, is one of the most quietly disturbing environments in the solar system. Not because it harbors danger in any conventional sense, not because it threatens us, not because it contains anything that science fiction has trained us to fear, but because it is real, and the reality of Pluto, examined honestly, is a place so far outside the boundaries of human physical experience that every attempt to make it feel familiar eventually fails. Every analogy breaks down. Every comfortable comparison runs out of runway before it reaches the actual conditions of the surface and atmosphere. The numbers describing Pluto's environment are not just large or extreme in the way that superlatives are large or extreme. They describe conditions that fall entirely outside the range of anything the human body or the human mind evolved to intuitively process. This is what the Webb data revealed, not in a single dramatic announcement, but in layers, each layer more unsettling than the one before. Each measurement adding detail to a portrait that grows harder to look at the more complete it becomes. That portrait is what we are going to examine, not the cartoon, not the mascot, not the sentimental underdog of popular imagination, the real Pluto, and the truth of what the most powerful telescope ever built found when it finally looked. For nearly a century, the story of how humanity came to know Pluto has been a story of progressive disillusionment dressed up as discovery. Each new instrument, each new mission, each new generation of telescopes brought us closer to the actual physical reality of this world. And each time we got closer, the world we found was less familiar than the one we had imagined before. It began in the winter of 1930, at the Lowell Observatory in Flagstaff, Arizona. A 24-year-old astronomer named Clyde Tombaugh had been assigned a task that most of his colleagues considered tedious to the point of punishment. He was to systematically photograph sections of the night sky on glass photographic plates, then compare pairs of plates taken days apart, searching for any point of light that had shifted position against the fixed background of distant stars. Planets and other solar system bodies move. Stars, being incomparably farther away, do not. Any moving point of light was a candidate for something close enough to be gravitationally bound to our sun. Tombaugh worked through the photographs with a device called a blink comparator, a machine that rapidly alternated between two plates so that any moving object appeared to jump back and forth. The work required extraordinary patience and a tolerance for monotony that few people possess. He examined millions of star images over the course of months. On February 18th of 1930, a small point of light jumped. It was faint, nearly at the limit of detection, and it moved exactly as an object orbiting far beyond Neptune should move. Tombaugh had found something. The announcement made international headlines. The solar system had a new planet, or so the world believed for the next 76 years. The naming of the new world fell to an 11-year-old schoolgirl in Oxford, England, named Venetia Burney, who suggested Pluto after the Roman god of the underworld. The name was fitting in ways that nobody at the time fully appreciated. Pluto was a lord of darkness, a ruler of the realm beneath, a figure associated with cold and shadow and the absolute absence of warmth. The world that bore his name would turn out to embody all of these qualities to a degree that the mythology itself barely suggested. In the decades following its discovery, Pluto remained almost entirely mysterious. It was so remote and so small that even the finest ground-based telescopes of the mid-20th century could resolve it only as a faint, unresolved point of light. Scientists could calculate its orbital parameters with reasonable precision. They knew it traced an eccentric elliptical path, inclined significantly relative to the plane in which the other planets orbit, and that this path required 248 Earth years to complete. They could estimate its approximate distance from the Sun at different points in its orbit. Beyond that, almost nothing was certain. The size estimates in those early decades were consistently wrong, and consistently wrong in the same direction. Pluto was repeatedly thought to be larger than it turned out to be. Early calculations suggested it might be comparable in size to Earth. Later revisions brought the estimate down to something comparable to Mars. The actual diameter, eventually confirmed to be approximately 2,377 kilometers, was not firmly established until the late 20th century. Pluto is smaller than Earth's moon. Its diameter is roughly 2/3 the width of the lunar disk. If you were to place Pluto directly over the continental United States, it would extend approximately from the eastern seaboard to somewhere near the Texas border, no farther. This is not a large world. It is not even a medium-sized world by the standards of our solar system. It is a small body, geologically ancient, gravitationally modest, orbiting in a region of space where most things are cold and dark and unremarkable. This smallness fed the sentimental image in ways that were difficult to avoid. A world that compact simply does not seem threatening. It does not seem important. It seems, almost inevitably, like the kind of object to which people feel protective rather than awed. An underdog by virtue of its dimensions alone, before anyone knew anything meaningful about what it actually was. In 1978, astronomers James Christie and Robert Harrington, working at the United States Naval Observatory, noticed something unusual in elongated photographic images of Pluto. The planet appeared to have a bulge that shifted position from image to image. The explanation was a large moon orbiting at very close range. The moon was named Charon, after the ferryman of the dead in Greek mythology, the figure responsible for transporting souls across the river that separated the living world from the underworld. Charon orbits Pluto at a distance of only approximately 19,600 kilometers and is so large relative to its host, with a diameter roughly half that of Pluto itself, that astronomers immediately recognized the system as something unusual. The two bodies are gravitationally locked such that the same hemisphere of each always faces the other. They do not orbit in the conventional sense of a small moon circling a large planet. They orbit each other, rotating together around a common center of gravity that lies in the space between them. Two frozen worlds bound together in permanent mutual regard, circling through the outer dark as a pair. This discovery complicated the simple image of Pluto as a solitary wanderer, but it did not fundamentally alter the public's relationship with the dwarf planet. If anything, it made the picture more poignant. Pluto was no longer alone. It had a companion. The romantic quality of the mythology reinforced itself. The lord of the underworld and the ferryman of souls, together in the cold beyond Neptune. It was not a scientific narrative so much as a story that people told themselves about what the data meant, which is different. In the following decades, 4 additional small moons were confirmed in the Pluto-Charon system: Nix, Hydra, Kerberos, and Styx. Each tiny, each irregular in shape, each probably composed largely of water, ice, and silicate rock. Their existence added complexity to the system without substantially clarifying the nature of Pluto itself. Scientists also detected the first convincing evidence of an atmosphere through a technique called stellar occultation, in which Pluto passes in front of a distant background star, and the star's light is refracted and dimmed by atmospheric gas before being cut off by the solid body. The pattern of dimming and brightening on either side of the occultation event carries a signature that can reveal atmospheric pressure and composition. Early occultation measurements confirmed that Pluto possessed a thin gaseous envelope composed primarily of nitrogen with traces of methane and carbon monoxide. The surface pressure was measured in fractions of a Pascal. By any engineering definition, this was not an atmosphere. It was an atmospheric suggestion, a wisp so thin that it would qualify as a high-grade laboratory vacuum on Earth. Yet even this vapor made Pluto more interesting than a completely airless rock. It meant that something was happening on the surface. Ices were sublimating. Volatile materials were entering a gaseous phase and rising above the surface, however briefly, before recondensing somewhere else. The planet was not entirely static. It was doing something, even if that something was too subtle and too slow for the instruments of the time to characterize in any useful detail. The Hubble Space Telescope, launched in 1990 and refined in subsequent servicing missions, brought the first genuine improvement in spatial resolution. By the mid-2000s, Hubble's most capable instruments could resolve Pluto as a small disk rather than a point of light. Surface maps constructed from careful analysis of Hubble data revealed a world with distinct light and dark regions. The bright areas were tentatively associated with fresh volatile ice deposits. The darker areas were suspected to be older terrain coated in organic compounds. There was structure, there was variation, but there was no clarity. The maps looked like blurry watercolors, suggestive of geography without being able to confirm it. Pluto remained, even through Hubble's eye, a world of hints rather than facts. What scientists needed was not a better telescope in Earth orbit. They needed a spacecraft at close range. They needed to bridge the 5 billion kilometer gap between Earth and Pluto and deliver an instrument package to within tens of thousands of kilometers of the surface. The mission that would do this was approved by NASA in 2001, launched in January of 2006, and given the name New Horizons. New Horizons carried 7 scientific instruments packed into a compact spacecraft, roughly the size and shape of a grand piano. It was powered by a radioisotope thermoelectric generator, a device that converts the heat produced by the radioactive decay of plutonium dioxide into electrical power. There is a specific kind of symmetry in the fact that the mission to Pluto was powered by plutonium. The spacecraft crossed the orbit of Jupiter in early 2007 and used that giant planet's gravitational field to accelerate to a final cruise velocity of approximately 50,000 kilometers per hour. At that speed, a human being could travel from New York to Los Angeles in just over 4 minutes. Even so, the journey to Pluto took 9.5 years. The distances involved in reaching the outer solar system are not merely large. They are in a category of spatial scale that resists intuitive compression. New Horizons reached its closest approach to Pluto on the 14th of July 2015, passing within approximately 12,500 kilometers of the surface. The flyby window during which the most detailed measurements could be taken lasted only a few hours. The spacecraft was moving too fast to slow down. There was no orbital insertion, no leisurely survey, no opportunity to circle back for a second look. New Horizons screamed through the Pluto-Charon system at full speed, its instruments recording everything they could in the brief window of opportunity, and then continued outward into the Kuiper belt on a trajectory that would eventually carry it beyond the solar system entirely. The images and data that the spacecraft returned over the following months transformed the scientific understanding of Pluto completely. The photographs were extraordinary. The surface was not the undifferentiated frozen terrain that cautious scientists had half expected. It was a world of remarkable geological diversity, bearing evidence of processes that nobody had anticipated finding on a body so small, so cold, and so far from the sun. The western hemisphere of Pluto's near side was dominated by an enormous bright feature, informally named Tumbor Regio, in honor of the man who had found the planet 85 years earlier. Within that feature sat a vast smooth basin, approximately 1,000 kilometers across, subsequently named Sputnik Planitia, filled with nitrogen ice of such freshness and geological youth that it displayed almost no impact craters at all. The surface of the basin was organized into a mosaic of irregular polygonal cells, each tens of kilometers across, separated by shallow troughs. These cells were the surface expression of convective overturn, warmer nitrogen ice rising from depth, spreading across the surface, cooling, and sinking again in a cycle that refreshed the landscape continuously on timescales estimated at roughly 500,000 years. The basin was geologically alive, not in any biological sense, but in the sense that physical processes were actively reshaping it on timescales short enough to erase the cratering record that would otherwise accumulate over billions of years. Surrounding the nitrogen plains, mountain ranges of water ice rose several kilometers above the surrounding terrain. These mountains were not geological curiosities. They were structurally fundamental to understanding Pluto's physical character. At temperatures of around -230 degrees Celsius, water ice becomes as rigid and mechanically strong as terrestrial rock. It does not flow under its own weight. It does not deform slowly like a glacier. It behaves like bedrock, forming the permanent structural framework of Pluto's crust, upon which the softer, more volatile ices migrate and transform. The mountains were water ice standing in for granite. The valleys and plains were nitrogen and methane standing in for soil and sediment. Everything familiar about a planetary surface was present, but constructed entirely from materials that on Earth are invisible atmospheric gases. On the hemisphere facing away from the heart-shaped feature, the surface character changed dramatically. Dark reddish bands stretched across the equatorial regions, coated in materials called tholins. These are complex organic compounds produced when ultraviolet radiation from the sun breaks apart simpler molecules like methane and nitrogen in the upper atmosphere, and the resulting molecular fragments reassemble into increasingly large and complex structures that eventually condense as solid particles and drift slowly down to the surface. Tholins are not exotic laboratory curiosities. They are among the most common organic compounds in the outer solar system. They coat the surfaces of numerous moons, dwarf planets, and small bodies throughout the Kuiper belt. They are reddish-brown, they are sticky, they absorb ultraviolet radiation efficiently, and they are chemically complex enough that some researchers have speculated about their potential relevance to prebiotic chemistry. On Pluto, they stain the terrain in patterns that track the atmospheric photochemistry operating hundreds of kilometers above the ground. And above all of it hung the haze. When New Horizons looked back at Pluto after its closest approach, capturing a backlit image of the planet against the distant stars, the photograph revealed something that had not been fully anticipated. The atmosphere was not a simple, featureless envelope. It was layered, structured, extending far higher above the surface than models had predicted, and it scattered sunlight in the shorter blue wavelengths in a way that gave the atmospheric column a distinct blue tint visible against the blackness of space. the haze appeared to extend in discrete layers to altitudes of over 200 kilometers, and perhaps significantly higher in some regions. It was delicate-looking, gossamer, the kind of visual detail that photographers arrange and light for maximum effect. But it was also made of organic poison, suspended in a near vacuum, and its presence raised questions that the New Horizons flyby was not equipped to answer. This is the point at which the limitations of a single flyby become scientifically critical. New Horizons was a reconnaissance mission. Its purpose was to obtain the first close-range observations of a world that had never been seen at close range, to determine what Pluto looked like, what its surface was made of, what its atmosphere contained, and what geological processes had shaped its terrain. It accomplished all of these objectives with extraordinary success, but a reconnaissance mission, by definition, obtains a snapshot. It captures one moment, one configuration, one set of conditions prevailing on a single date. It cannot watch the system change. It cannot measure how processes evolve over time. It cannot observe in wavelengths for which its instruments were not designed. New Horizons carried cameras optimized for visible and near ultraviolet light, a near-infrared spectrometer, an ultraviolet spectrometer, and several instruments designed to measure the plasma environment and dust population rather than the surface directly. These instruments were extraordinarily well suited to the mission's core objective. They were not suited to measuring Pluto's thermal emission in the mid-infrared wavelengths, where the planet's coldest and most fundamental physical processes reveal themselves most clearly. Mid-infrared observations of Pluto were not simply absent from the New Horizons dataset. They were physically impossible for New Horizons to obtain. The spacecraft carried no mid-infrared instrument because no mid-infrared instrument compact and power-efficient enough for a deep space mission of that kind existed at the time of the spacecraft's design and construction. The result was a gap in the scientific record that the stunning New Horizons photographs concealed more effectively than anyone quite appreciated in the immediate aftermath of the flyby. The images were so beautiful, so rich in detail, so far beyond anything previously available, that they created a widespread impression that Pluto was now understood, that the major questions had been answered, that what remained was a matter of interpretation and refinement rather than fundamental discovery. That impression was wrong. The most important physical process governing Pluto's climate was invisible to New Horizons. The thermal behavior of the surface and atmosphere, the detailed temperature distribution across the globe, the spectral signature of the atmospheric haze in wavelengths where its radiative activity becomes detectable. All of this lay entirely outside what New Horizons could see. It was as if a photographer had taken a superbly detailed portrait of a person's face while remaining completely unable to measure their body temperature, blood chemistry, or neural activity. The portrait was genuine. The information it contained was real. But the portrait was not the person, and the gaps in the record were as significant scientifically as everything the portrait revealed. To access what New Horizons could not measure required an instrument of a fundamentally different kind. It required a telescope with a mirror large enough to collect sufficient light from an object as faint and as distant as Pluto in wavelengths where Pluto's thermal signal is at its most diagnostic. It required detectors sensitive enough to register emission from a surface hovering near 40 Kelvin at a distance of nearly 5 billion kilometers. It required spatial resolution sufficient to disentangle the overlapping thermal signals of Pluto and Charon, two bodies separated by only 19,600 kilometers as seen from Earth's distance, a gap so small that every previous mid-infrared instrument had blurred them into a single, unresolvable source. The instrument that met all of these requirements had been under development for decades by the time New Horizons flew past Pluto. Its primary mirror was 6.5 meters in diameter. Its detectors were cooled to within a few degrees of absolute zero to minimize thermal noise. It was designed to operate in infrared wavelengths, ranging from just beyond the visible all the way into the mid-infrared, where objects as cold as Pluto emit the bulk of their thermal radiation. It was placed not in low Earth orbit, like Hubble, but at a gravitationally stable point called the second Lagrange point, approximately 1.5 million kilometers from Earth, in the direction away from the Sun where it could maintain a stable cold temperature and observe the universe without Earth's thermal interference. It was called the James Webb Space Telescope, and when it turned its instruments toward Pluto, it did not find what the sentimental image had led anyone to expect. To understand what the James Webb Space Telescope revealed about Pluto, you need to understand the difference between seeing a world and measuring one. These are not the same thing. They have never been the same thing. And the confusion between them is responsible for much of the gap between the popular image of Pluto and its physical reality. When you look at a photograph of Pluto taken by New Horizons, you are seeing reflected sunlight. Photons that left the surface of the sun 8 minutes earlier traveled nearly 5 billion kilometers, struck Pluto's surface, and bounced back toward the spacecraft's cameras. The image that results tells you what the surface looks like in roughly the same wavelengths your own eyes would register if you were floating above the landscape. Bright regions reflect more sunlight. Dark regions absorb more. Color variations hint at compositional differences. The image is genuine, informative, and visually extraordinary. It is also, in the most physically precise sense of the word, superficial. It shows you the appearance of the surface. It tells you almost nothing about what the surface is doing. Mid-infrared observation is categorically different. In the mid-infrared, you are not detecting reflected light at all. You are detecting emitted heat. Every object in the universe with a temperature above absolute zero radiates thermal energy across a spectrum of wavelengths determined by that object's temperature. For objects as cold as Pluto's surface, hovering between approximately 40 and 60 Kelvin, the peak of this thermal emission falls in wavelengths between roughly 15 and 25 micrometers. This is well into the mid-infrared range, far beyond anything the human eye can detect, far beyond the capabilities of visible light cameras, and far beyond what New Horizons carried instruments to measure. What mid-infrared observations reveal is the thermal behavior of the surface and atmosphere, not what they look like, but how they are exchanging energy with their environment. Which regions are warmer and which are cooler. How quickly different surface materials heat up and cool down as the planet rotates. Whether the atmosphere is absorbing solar energy and releasing it as infrared radiation, and if so, at what altitudes and through what physical mechanisms. These questions are not peripheral to understanding Pluto. They are central. They are, in fact, the questions on which everything else about Pluto's climate depends. The James Webb Space Telescope's primary instrument for addressing these questions was MIRI, the mid-infrared instrument, a collaborative development between NASA and the European Space Agency that operates across wavelengths from approximately 5 to 28 micrometers. MIRI was cooled to approximately 6.5 Kelvin, colder than the surface of Pluto itself, using a dedicated cryocooler system. This extreme cooling was necessary to suppress the instrument's own thermal noise to a level where signals as faint as Pluto's mid-infrared emission could be detected at all. The engineering required to achieve this represented decades of development across multiple institutions on 2 continents. The result was an instrument of sensitivity that had no precedent in the history of space-based infrared astronomy. MIRI faced a specific challenge with Pluto that no previous mid-infrared instrument had overcome. As viewed from Earth's position nearly 5 billion kilometers away, Pluto and Charon are separated by an angular distance so small that previous instruments with coarser spatial resolution blurred their combined thermal signal into a single, unresolvable source. It was impossible to determine which fraction of the observed infrared emission came from Pluto and which came from Charon. The 2 worlds were thermally indistinguishable to every instrument that had previously attempted to measure them. This was not merely an inconvenience. It meant that any attempt to model Pluto's climate using existing mid-infrared data was fundamentally compromised by uncertainty about how much of the measured signal actually belonged to the planet being studied. Webb's combination of primary mirror diameter and precise infrared optical design gave MIRI just sufficient spatial resolution to begin separating the 2 thermal sources. The separation was not visual in the sense of producing distinct images of 2 distinct disks. It was photometric. By carefully modeling the known orbital geometry of the Pluto-Charon system, tracking how the combined brightness shifted as the two bodies moved relative to each other during extended observations, and applying precise calibration to the telescope's point spread function, researchers could extract the individual thermal contributions of each body from the blended signal. It was the astronomical equivalent of isolating two voices recorded simultaneously on a single microphone by exploiting known differences in their timing and pitch. The observations were conducted in two phases. In 2022, Webb's MIRI instrument measured the thermal emission from the Pluto Charon system at wavelengths of 18, 21, and 25 micrometers. These measurements captured how the combined infrared brightness varied as both bodies rotated, revealing thermal light curves that encoded information about temperature differences across their respective surfaces. The data required careful reduction and analysis to extract meaningful physical parameters, a process that took months of computational work by teams distributed across France, the United States, and several European research institutions. In 2023, MIRI obtained a complete mid-infrared spectrum of Pluto, spanning wavelengths from approximately 4.9 to 27 micrometers. This was the first time in the history of planetary science that anyone had measured Pluto's thermal emission across this full spectral range. Previous instruments operating from Earth orbit or from the surface simply could not detect a signal this faint from an object this cold at this distance. The thermal emission from Pluto's surface and atmosphere at these wavelengths is extraordinarily weak, diluted by the immense distance and competing against the instrument's own residual noise floor. Only Webb's combination of mirror size, detector sensitivity, and orbital position made the measurement achievable. The results of both observation campaigns were published in 2025 across multiple papers in the journals Astronomy and Astrophysics and Nature Astronomy. The lead author on the primary analysis was Emmanuel Lelouch, a planetary scientist at the Paris Observatory with decades of experience in the spectroscopic study of outer solar system bodies. The findings his team reported represented, by any reasonable measure, a fundamental revision in the scientific understanding of how Pluto functions as a physical system. The first and most consequential result was the confirmation of a hypothesis that had been published 8 years earlier and that had remained unverifiable in the absence of exactly the kind of data Webb had now obtained. In 2017, a team led by Shi Zhang at the University of California, Santa Cruz had proposed something radical about Pluto's atmosphere. They argued, based on theoretical modeling, that the organic haze suspended in Pluto's upper atmosphere was not merely a byproduct of atmospheric photochemistry. It was the primary driver of Pluto's climate. The haze particles, they argued, were absorbing ultraviolet radiation from the sun, warming slightly, and then radiating that absorbed energy away as infrared emission. This process, they calculated, would cool the atmospheric column far more efficiently than nitrogen and methane gas alone could manage. If correct, it would explain a puzzling discrepancy in the New Horizons temperature data. When New Horizons measured Pluto's atmospheric temperature profile during its flyby, it found that the upper atmosphere was dramatically colder than existing models had predicted. At altitudes of several hundred kilometers, the temperature was approximately 70 degrees Celsius, below what gas phase cooling models suggested it should be. Something was extracting heat from the atmosphere at a rate that the molecular behavior of nitrogen and methane gas could not account for. The discrepancy was large enough that it could not be attributed to measurement error or model uncertainty. Something real was cooling Pluto's atmosphere more effectively than anyone had calculated. Zhang and his colleagues proposed the haze as the answer. Their models showed that if the haze particles were radiatively active, absorbing solar ultraviolet and remitting the energy as mid-infrared radiation, the net cooling effect would be consistent with the anomalously low temperatures New Horizons had measured. They published specific quantitative predictions about how bright Pluto should appear, in particular mid-infrared wavelengths, if the haze were operating as they proposed. These predictions were precise enough to be tested. All that was required was an instrument capable of detecting Pluto's mid-infrared emission with sufficient sensitivity and spectral resolution to compare the measured brightness against the predicted values. No such instrument existed in 2017. The Webb telescope was still under construction, years behind schedule, facing ongoing technical challenges and budget overruns that had at various points threatened the mission's survival. Zhang and his colleagues published their predictions and waited. The scientific community regarded the hypothesis with interest but appropriate skepticism. It was elegant, it was physically plausible, it resolved a genuine observational problem, but it remained unconfirmed. And in planetary science, unconfirmed hypotheses have a long history of turning out to be wrong in ways that seemed unlikely at the time. Webb changed that. When Lelouch's team extracted Pluto's mid-infrared spectrum from the 2023 MIRI observations and compared the measured brightness values against the predictions Zhang's group had published 6 years earlier, the agreement was striking. The thermal emission from Pluto's atmosphere in the wavelengths most sensitive to haze particle radiation matched the model predictions with a precision that the lead researcher described as rare in planetary science. The haze was glowing in the infrared. The organic particles suspended in Pluto's upper atmosphere were absorbing sunlight and re-emitting it as thermal radiation, cooling the atmospheric column exactly as the 2017 hypothesis had proposed. To appreciate the significance of this confirmation, consider what it means physically. On every other world in our solar system where we have characterized the atmospheric energy balance in any detail, the climate is driven by one of a small number of familiar mechanisms. On Earth, solar energy warms the surface. Surface contact and convection warm the lower atmosphere, and greenhouse gases modulate how efficiently heat escapes to space. On Mars, a thin carbon dioxide atmosphere responds to surface heating and drives dust storms that can envelop the entire planet. On Venus, a dense carbon dioxide atmosphere creates a runaway greenhouse effect that heats the surface to temperatures capable of melting lead. On Titan, a thick nitrogen atmosphere with organic haze layers is dense enough that gas phase dynamics dominate the energy balance. On every one of these worlds, the atmosphere's thermal behavior is governed by processes rooted in the physical properties of atmospheric gases. Pluto's atmosphere contains gases. Nitrogen, methane, and carbon monoxide are all present, but the gases are present in quantities so small, at pressures so negligible, that their contribution to the atmospheric energy balance is minor. The mid-infrared data confirmed that the dominant agent controlling atmospheric temperature is not a gas at all. It is a suspension of solid organic particles, a fraction of a micrometer in size, drifting through a column of near vacuum, hundreds of kilometers tall, absorbing ultraviolet photons and broadcasting the energy back into space as infrared light. This is a new kind of climate. Tanguy Bertrand, one of the researchers involved in the analysis, used precisely that phrase in describing the result. A new kind of climate, without analog anywhere else in the solar system that has been characterized by direct observation. On Pluto, the atmosphere is cooled not from within by the radiative properties of its constituent gases, and not from below by contact with a warm surface, but from above by a suspended layer of organic material that acts as a radiative exhaust system, drawing energy out of the atmospheric column and dumping it into space. The architecture of this climate inverts the logic that applies everywhere else we have looked. On Earth, climate is driven from the bottom up. The sun warms the ground warms the air, and convection carries heat upward from below. On Pluto, the sun's energy is intercepted at altitude by haze particles before it can reach the surface, converted into thermal emission and radiated outward. The ground plays almost no role in the atmospheric energy budget. The surface is too cold, the atmosphere too thin, and the solar input too feeble for any surface-driven process to compete with what the haze does overhead. Remove the haze from Pluto's atmosphere, and the temperature profile of the entire atmospheric column would look fundamentally different. The upper atmosphere would be warmer, or at least less anomalously cold. The energy balance would shift. The volatile cycle would be affected. The character of the world would change in measurable ways. The haze is not a secondary feature of Pluto's environment. It is the engine of the climate. And it operates in a regime that no planetary scientist, before the development of the theoretical models that Webb subsequently confirmed, had identified as a possibility for any world in our solar system. But the confirmation of the haze cooling hypothesis, remarkable as it was, represented only the outermost layer of what the Webb data contained. Beneath that layer, the mid-infrared observations encoded information about Pluto's surface thermal behavior that proved, when unpacked, to be more complex and more revealing than the atmospheric result alone. The thermal light curves captured by MIRI as Pluto rotated did not merely confirm that the planet was cold and that its haze was radiatively active. They painted a picture of a surface in constant, slow chemical and physical transformation, driven by processes that the visible light photographs from New Horizons had hinted at but never been able to characterize in this dimension. That picture, and what it implies for the future of Pluto's atmosphere, is where the story becomes genuinely difficult to sit with. Because what the thermal data shows is not a world in stable equilibrium with its environment. It shows a world in transition. A world whose climate is actively changing, decade by decade, in response to an orbital geometry that is slowly withdrawing it from the minimal warmth of a sun that was never more than a distant point of light to begin with. The haze is real. The cooling is real. The mechanism is confirmed. And the same mechanism that makes Pluto's climate unique in the solar system may also be the mechanism that is helping to dismantle it. The numbers that arrived from Webb's MIRI instrument were not photographs. They were not images in any sense that a non-scientist would immediately recognize as informative. They were flux measurements, quantitative records of how much infrared energy reached the telescope's detectors at specific wavelengths during specific intervals of time, calibrated against known reference sources and corrected for instrumental effects, atmospheric interference from Earth, and the complex geometry of the Pluto-Charon system as it rotated through the observation window. To a casual observer, the raw output would resemble nothing more than columns of numbers with associated uncertainty values. To a planetary scientist with the appropriate theoretical framework, those numbers were a transmission from a world that had never before communicated in this particular frequency. The thermal light curves were the first layer of that transmission to be decoded. As Pluto rotated during the hours of Webb observation, MIRI recorded how the total mid-infrared brightness of the system shifted. Because the telescope could partially resolve Pluto from Charon using the photometric separation technique described earlier, researchers could track not just the combined brightness but the individual contributions of each body as different surface regions rotated into and out of the instrument's line of sight. What they found was that Pluto's thermal emission was not uniform. It varied substantially as the planet turned, in patterns that traced the distribution of chemically distinct surface materials across the globe with a clarity that no previous measurement technique had achieved. When the vast nitrogen ice plains of Sputnik Planitia rotated to face the telescope, the mid-infrared signal shifted in one direction. When the dark, tholin-coated equatorial terrain came into view, the signal changed character measurably. When methane-rich highland regions dominated the visible hemisphere, the thermal curve shifted again. Each surface type produced a distinct infrared signature, a consequence of differences in what physicists call thermal inertia. This is a measure of how quickly a surface material responds to changes in heating rate. A material with high thermal inertia warms slowly when illuminated and cools slowly when shadowed. A material with low thermal inertia responds rapidly, swinging between temperature extremes as conditions change. On Earth, the contrast between ocean and desert illustrates the concept. Coastal regions experience mild, stable temperatures because seawater's high thermal inertia buffers against rapid temperature swings. Continental interiors bake in summer and freeze in winter because dry rock and soil respond quickly to changes in solar input. The same principle operates on Pluto, but expressed through materials that bear no resemblance to anything in a terrestrial landscape. Nitrogen ice has a relatively low thermal inertia, meaning it responds quickly to the tiny fluctuations in solar input that Pluto experiences as it rotates. Methane ice behaves differently, with thermal characteristics that cause it to retain absorbed energy for longer before re-radiating it. Water ice bedrock, being structurally rigid and compositionally distinct from the volatile surface layers, has different thermal properties again. and the tholin-coated dark terrain absorbs incoming radiation efficiently and remits it on its own schedule, darker than the bright ice regions and therefore warmer despite receiving the same feeble solar input. Webb's ability to measure these thermal inertia differences across Pluto's surface matters enormously for understanding the planet's climate, because thermal inertia governs how volatile ices migrate. The volatile cycle on Pluto is the central physical process that determines the distribution of surface materials, the character of the landscape at any given moment in the planet's long orbit, and the rate at which the atmosphere is sustained or depleted. To understand the volatile cycle is to understand Pluto. And to understand Pluto's volatile cycle, you need to know not just where the ices are, but how they respond thermally to the environment they occupy. Here is how the volatile cycle works, and why the Webb thermal data made it visible in a way that was not previously possible. Nitrogen is the dominant volatile species on Pluto's surface, and the primary constituent of its atmosphere. At the temperatures prevailing on Pluto's surface, nitrogen exists as a crystalline solid, but solid nitrogen at these temperatures is not entirely stable. When sunlight strikes it, even the impoverished trickle of solar energy arriving at Pluto's distance, a small fraction of the nitrogen molecules at the surface absorb enough thermal energy to break free of the crystal lattice and enter the gaseous phase directly, without passing through a liquid intermediate. This process is called sublimation. On Earth, you observe it when dry ice, which is solid carbon dioxide, appears to smoke in warm air. The solid converts directly to vapor. On Pluto, nitrogen does the same thing, but at temperatures so extreme and under conditions so different from anything terrestrial that the comparison barely does justice to the strangeness of the process. The nitrogen vapor that enters the atmosphere from sublimating surface ice contributes to the thin gaseous envelope that constitutes Pluto's atmosphere. As the planet rotates and different regions are illuminated or shadowed, the balance between sublimation and condensation shifts. Sunlit regions sublimate nitrogen and lose surface ice. Shadowed regions are colder and receive nitrogen vapor transported through the atmosphere, which recondenses as fresh frost. Over time, nitrogen migrates from one part of the surface to another, carried not by rivers or wind in any terrestrial sense, but by the global circulation of an atmosphere so thin that each individual molecule travels enormous distances before encountering another. Pluto's extreme axial tilt, approximately 120 degrees relative to its orbital plane, meaning the planet orbits essentially on its side, ensures that different hemispheres receive dramatically different solar illumination at different points in the 248-year orbital cycle. During certain phases of the orbit, one pole is illuminated continuously for decades, while the other sits in perpetual darkness. The illuminated pole sublimates volatile ices into the atmosphere. The dark pole serves as a cold trap, condensing those volatiles back onto the surface as frost. Over the course of a full orbit, the distribution of surface ice shifts substantially, driven by this hemispheric imbalance. Sputnik Planitia, the great nitrogen ice basin, functions as a particularly efficient component of this system. Its lower elevation relative to the surrounding terrain means that atmospheric pressure at the basin floor is slightly higher than elsewhere, creating conditions slightly more favorable for nitrogen condensation. The basin therefore acts as a preferential accumulation site, drawing nitrogen from other regions and maintaining its distinctive fresh, crater-free surface, while the surrounding terrain experiences net nitrogen loss. The result is a landscape whose major features are not geological in the conventional sense of being produced by volcanism, tectonics, or erosion. They are climatological. They are the surface expression of a volatile cycle operating on orbital timescales. What Webb's thermal data added to this picture was the ability to see how different ice species were participating in the cycle simultaneously, and how their thermal signatures differed in ways that revealed their physical state, rather than just their chemical identity. Methane, the second most abundant volatile species, behaves differently from nitrogen in ways that the mid-infrared spectrum made newly legible. Methane is less volatile than nitrogen, meaning it requires slightly more energy to sublimate and tends to remain frozen under conditions where nitrogen would already be entering the gaseous phase. This difference in volatility causes methane to concentrate in different locations than nitrogen, accumulating preferentially on higher elevation terrain, where the thermal environment differs subtly from the low-lying basins. New Horizons had already established this pattern in broad outline, showing methane ice concentrated on mountain peaks and ridgelines, while nitrogen filled the valleys. But Webb's thermal observations added a dimension that the visible light photographs could not provide. The mid-infrared spectrum of methane-rich regions suggested that the methane ice on Pluto's surface is not texturally uniform. Different areas appeared to contain methane in different physical forms, with variations in crystal size and surface roughness that affected how quickly those regions responded to changes in solar input. Areas with large methane crystals behaved differently from areas with fine-grained methane frost, heating and cooling on different timescales, participating in the volatile cycle at different rates. This textural heterogeneity had never been directly measured before Webb. Its existence implies that the surface Pluto presents to the universe at any given moment is not simply a map of chemical composition, but a record of the physical history of each region. How long has the methane in this location been accumulating? Has it been disturbed by recent sublimation events? Has it been buried under nitrogen frost and then re-exposed? The thermal data encodes answers to these questions in ways that compositional spectroscopy alone cannot provide. Carbon monoxide, the third major volatile, added further complexity. Intermediate in volatility between nitrogen and methane, carbon monoxide tends to be mixed with nitrogen ice in the large basin regions rather than segregated onto distinct terrain types. Webb's spectral sensitivity was sufficient to detect carbon monoxide's thermal contribution within the broader nitrogen ice signal, revealing that it participates in the global transport cycle with its own timing and spatial distribution. The interplay between three chemically distinct volatile species, each with different physical properties and different responses to the thermal environment, produces a surface chemistry of considerable complexity that simple models of a two-component volatile system had never fully captured. The thermal light curves also revealed something about the contrast between Pluto's illuminated and shadowed hemispheres that illuminated the pace of surface change. On a world with a simple uniform surface and no atmosphere, the thermal curve as the planet rotated would be smooth and predictable. Illuminated regions would be slightly warmer than shadowed regions, and the transition between them would follow a gradual sinusoidal pattern tied to the rotation period. Pluto's thermal curve was neither smooth nor predictable. It was irregular, punctuated by distinct features that corresponded to specific surface regions coming into view. The nitrogen ice plains produced one signature. The tholin-stained equatorial bands produced another. The methane highlands produced a third. The curve was a fingerprint of the surface's chemical heterogeneity, readable only in the mid-infrared wavelengths that Webb could access. For the first time, scientists had an instrument capable of monitoring Pluto's surface thermal behavior over multiple observation epochs. A single set of measurements, however detailed, tells you the state of the system at one moment. Repeated observations over years and decades will reveal how the thermal map changes as Pluto continues to recede from the Sun, as volatile ices redistribute in response to shifting illumination patterns, as the atmosphere thins and the volatile cycle slows. New Horizons gave science a portrait. Webb is beginning to give it a time-lapse. And then there was Charon. The ability to separate Charon's thermal signal from Pluto's, even partially, allowed researchers to characterize Pluto's largest moon in mid-infrared wavelengths for the first time. What those measurements revealed about Charon was unexpected in its clarity, and what it implied about the relationship between the two bodies was, in the precise sense of the word, eerie. Charon is a very different world from Pluto. Its surface is dominated by water ice mixed with ammonia-bearing compounds. It lacks the volatile nitrogen, methane, and carbon monoxide ices that drive Pluto's climate. It has no atmosphere detectable by any current instrument. Its thermal behavior is that of an inert, icy surface responding passively to the solar radiation it receives, warming slightly on the illuminated side and cooling on the shadowed side with no atmospheric mediation of any kind. In most respects, Charon is precisely what the popular image of Pluto incorrectly imagines Pluto to be: a geologically simple, chemically unremarkable, atmospherically dead, icy body drifting in the cold. But Charon's polar regions are not unremarkable. They are dark, they are reddish, and they are stained with organic material that has no local source. New Horizons had photographed these polar caps in 2015, and their unusual coloration had been noted and debated. The leading hypothesis at the time was that Pluto's escaping atmospheric methane was responsible. Methane molecules leaving Pluto's upper atmosphere at sufficient velocity to escape the planet's gravitational hold would drift through the space between the two worlds. Some fraction of those molecules would encounter Charon's surface and freeze there, accumulating over long periods during Charon's polar winters, when temperatures at the poles fall to approximately 15 Kelvin. When polar spring eventually returned and sunlight reached those accumulated methane deposits, ultraviolet radiation would drive photochemical reactions that converted the methane into progressively heavier organic compounds, ultimately producing reddish tholin-like material, similar to what coats Pluto's own equatorial terrain. This was an appealing hypothesis. It explained the coloration. It connected Charon's surface chemistry to Pluto's atmospheric escape in a physically coherent way. But it was a hypothesis based on indirect evidence and theoretical plausibility. Confirming it required detecting the specific chemical signatures of radiation-processed organic material on Charon's surface in wavelengths diagnostic of those compounds. Webb provided that confirmation. Earlier near-infrared spectroscopic observations from Webb, published in 2024, had already detected carbon dioxide and hydrogen peroxide on Charon's surface, molecules that had never previously been identified there. Carbon dioxide most likely forms through radiation-driven reactions involving carbon monoxide and water ice in Charon's surface layers. Hydrogen peroxide arises from the radiolytic decomposition of water, ice bombarded by solar ultraviolet radiation, and energetic particles from the solar wind. These detections were consistent with an active surface chemistry driven by radiation processing of simple ices, but they did not by themselves confirm that Pluto's escaping methane was the primary feedstock for Charon's organic polar caps. The thermal data from MIRI added another piece to this picture. By characterizing the thermal properties of Charon's polar regions in mid-infrared wavelengths for the first time, the thermal signature of the dark polar material differed measurably from that of Charon's brighter equatorial terrain, consistent with the presence of a low albedo organic coating with distinct thermal inertia from the underlying water ice. The measurements were consistent with the accumulated tholin hypothesis and helped constrain the thickness and distribution of the organic layer in ways that near-infrared spectroscopy alone could not. Taken together, the Webb data confirmed something about the Pluto-Charon system that has no parallel anywhere else in our solar system. Pluto is continuously leaking processed atmospheric material onto its own moon. Methane escapes from Pluto's atmosphere, crosses nearly 20,000 kilometers of vacuum, deposits on Charon's polar regions, undergoes chemical transformation driven by solar ultraviolet radiation, and is permanently incorporated into the moon's surface as complex organic compounds. The process has been operating for as long as Pluto has maintained a significant atmosphere, which means for a very long time. The dark reddish polar caps visible in New Horizons photographs are not a transient surface feature. They are the accumulated record of a one-directional chemical transfer operating across interplanetary space over geological timescales. No other planet in our solar system does this to its moons. Mars does not deposit atmospheric carbon dioxide onto Phobos or Deimos in any chemically meaningful way. Jupiter's interactions with its moons involve electromagnetic and plasma processes fundamentally different from the simple thermal escape and condensation mechanism operating between Pluto and Charon. Saturn's interaction with its moons through the planet's extensive magnetosphere bears no resemblance to what happens here. The Pluto-Charon chemical connection is unique. a consequence of the specific combination of properties that characterizes this system: a thin escaping atmosphere, rich in volatile organics, a close companion body with no atmosphere of its own to deflect incoming molecules, weak gravity on both bodies that makes escape and recapture relatively easy, extreme cold that causes whatever arrives on Charon to freeze immediately, and centuries-long polar nights that allow accumulated methane to remain frozen long enough for photochemical processing to proceed. It is a system that nobody would have designed from first principles, and that required both New Horizons and Webb to characterize with any real specificity. And it is, in the way that only genuinely strange physical realities can be, more disturbing than any fictional invention, not because it is dangerous, not because it threatens anything, but because it reveals that two worlds, 19,600 kilometers apart, are engaged in a slow, continuous chemical dialogue across vacuum, one speaking in escaped molecules and the other responding in accumulated organic stains, and that this conversation has been ongoing for longer than any human civilization has existed to observe it. The Webb data does not make this process feel familiar. It makes it feel inevitable. Given the specific physical parameters of this system, everything that is happening between Pluto and Charon is exactly what the laws of physics and chemistry predict should happen. There is no mystery in the mechanism. The mystery lies only in the fact that it took this long to confirm it, and that the confirmation required an instrument of Webb's capability to achieve. The universe does not reveal its processes on human timescales or through human-scale instruments. It reveals them when the instruments finally become adequate to the task. And the task, as the Pluto-Charon data makes clear, is not yet finished. The thermal measurements confirm what is happening now. They constrain what has happened in the recent geological past. What they cannot directly answer is what will happen next, as Pluto continues its long retreat from the Sun and the conditions that sustain the volatile cycle, the haze, the atmospheric escape, and the chemical transfer to Charon all begin to change. That question, the question of what becomes of Pluto as its atmosphere enters an era of decline, is where the Webb data leads most directly and most uncomfortably. Because the answer, framed by the thermal measurements that have now confirmed how Pluto's climate actually works, is not a gentle seasonal transition. It is something considerably more final. Stand on the surface of Pluto at local noon. Take a moment to locate the Sun. It is there. You can find it if you know where to look, but it does not look like the Sun you have spent your entire life beneath. It does not fill any portion of the sky with warmth or brilliance. It does not cast the kind of light that makes you squint or raise your hand to shade your eyes. From Pluto's average orbital distance of approximately 39 astronomical units, the Sun has shrunk to a single intensely bright point of light set against a sky that remains functionally black even at the height of the local day. It is brilliant, in the way a distant searchlight is brilliant. You can see it clearly, you can identify its position with certainty, but it delivers almost nothing in the way of warmth. The total quantity of solar energy arriving at Pluto's surface is approximately 1/1500th of what falls on each square meter of Earth's surface at noon on a clear day. To place that number in terms that carry some intuitive weight, imagine standing inside an enormous stone cathedral in the middle of winter, with every window sealed and every source of heat removed. The cathedral is dark, except for a single candle flame burning at the far end of the nave, perhaps 50 meters away. You can see the flame clearly. You can confirm that it exists and that it is producing light, but you cannot feel it. The warmth it generates dissipates entirely before it crosses the distance between you and that distant point of fire. The stone floor beneath your feet remains as cold as the air. The walls radiate nothing back at you. The flame is real and visible, and completely without consequence for your thermal experience. That is the Sun from Pluto's surface. Visible, unambiguous, thermally irrelevant. This single physical fact, the near-total absence of usable solar warmth at Pluto's distance, is the foundation upon which everything else about the planet's environment is built. And it is the fact that the popular image of Pluto, assembled from photographs, adjusted for contrast and exposure to maximize visual detail, most thoroughly conceals. The New Horizons photographs look bright, because cameras designed to collect every available photon and render a visually interpretable image can make almost any illuminated surface look adequately lit. The human experience of standing in that same landscape would bear no resemblance to the photographs. The terrain would be visible but dim, bathed in a blue-tinged twilight that flattened colors and deepened shadows. The sky above would be black and filled with stars that remained visible throughout the local day because the atmosphere is far too thin to scatter sunlight into the blue glow that hides stars from Earth's daytime sky. The haze layers, so visually prominent in the backlit New Horizons images, would be invisible to any observer standing on the surface looking upward, too sparse and too finely distributed to produce any perceptible tint or glow from below. You would be standing on a world that is simultaneously illuminated and dark. A paradox of light without warmth, visibility without comfort, a sun without heat. Now consider what this means for temperature, and do so with the understanding that the numbers involved are not merely large in the way that superlatives are large. They describe conditions that fall entirely outside the range of anything the human body or the human mind evolved to intuitively process. Pluto's surface temperature varies between approximately 40 and 60 Kelvin, depending on location, surface composition, and the angle of solar illumination. Converted to more familiar scales, that range spans roughly -233 to -213 degrees Celsius, or approximately -387 to -352 degrees Fahrenheit. These numbers are so far below any temperature encountered in ordinary human experience that they resist comprehension through direct comparison. The coldest permanently inhabited place on Earth, the Siberian town of Oymyakon, reaches approximately -70 degrees Celsius in winter. The coldest temperature ever recorded on Earth's surface, at the Soviet Vostok station in Antarctica, was approximately -89 degrees Celsius. Pluto's surface is between 140 and 144 degrees colder than the coldest place ever measured on this planet. The gap between Pluto's surface temperature and the coldest point in Earth's recorded history is itself colder than the coldest winter night most people will ever experience. At these temperatures, the familiar categories of solid, liquid, and gas rearrange themselves in ways that require a complete revision of intuitive expectations. Nitrogen, the gas that constitutes 78% of every breath you draw on Earth, exists on Pluto's surface as a crystalline solid. It forms plains and glaciers and fills the Great Basin of Sputnik Planitia with a frozen expanse that flows under its own weight on geological timescales, in the same way that water ice flows as glaciers on Earth, but at temperatures more than 200 degrees colder than anything terrestrial ice ever experiences. Water, the substance most people instinctively associate with cold and ice, is frozen on Pluto so thoroughly and so permanently that it behaves not as ice in the familiar sense, but as structural bedrock. Water ice at 40 Kelvin does not flow, it does not deform under moderate stress. It does not participate in any volatile cycle. It simply sits in place, as rigid and immovable as granite, forming the permanent crust upon which the softer volatile ices migrate across the surface over centuries and millennia. Methane, the gas that burns in kitchen stoves and powers industrial furnaces, freezes into solid crystals on Pluto's highland ridges and mountain peaks. Carbon monoxide, a colorless, odorless poison gas on Earth, solidifies and mixes with the nitrogen ice across the basin floors. Every substance that exists as an invisible atmospheric gas at any temperature comfortable for human life has become a frozen mineral on Pluto's surface. The landscape is constructed from its own frozen sky. The ground beneath your hypothetical feet would be made of solidified atmosphere. The mountains on the horizon would be water ice standing in for granite. The frost patterns on the plains would be methane and carbon monoxide crystals condensed out of a gaseous envelope so thin that it barely registers as an atmosphere by any engineering standard. You would be walking on a world whose surface would literally evaporate if you could somehow warm it to temperatures that remain far below anything humans would describe as warm. The ground itself sublimates. Not metaphorically, not as a poetic description of some abstract geological process, but physically and measurably. Individual nitrogen molecules on the sun-facing surface absorb enough energy from that distant bright point to break free of the crystal lattice and enter the atmospheric gas phase, joining the thin column of vapor above, before eventually recondensing somewhere colder. The surface is transient. It is a temporary arrangement of frozen volatiles that rearranges itself continuously in response to the shifting geometry of light arriving from a star so far away that its warmth barely registers on the most sensitive instruments ever built. Webb's thermal data showed this process in action through the differing infrared signatures of ice species distributed unevenly across the surface. But the data also pointed towards something considerably more consequential than a description of current conditions. It pointed toward the trajectory along which those conditions are moving, and the direction of that trajectory is not toward greater stability or greater warmth. It is toward cold, toward stillness, toward the gradual shutdown of every process that makes Pluto's surface and atmosphere dynamic rather than inert. Pluto reached the closest point in its orbit to the Sun, a position astronomers call perihelion, in 1989, at a distance of approximately 29.7 astronomical units. This was the warmest Pluto had been in 248 years, and the warmest it would be for another 248 years. At perihelion, the increased solar energy drove sublimation of surface ices at the highest rate of the orbital cycle, inflating the atmosphere to its maximum extent and sustaining the volatile transport cycle at its greatest activity. The haze column was at its thickest. The methane escaping to Charon was at its highest flux. The surface ice redistribution was proceeding at its fastest pace. That peak has long since passed. Pluto is now on the outbound leg of its enormous elliptical orbit, receding from the Sun at a rate that will continue for well over a century before the orbit turns and begins the long approach back toward perihelion. As the distance from the Sun grows, the solar energy reaching the surface falls. Less energy means less sublimation. Less sublimation means less gas entering the atmosphere. Less atmospheric gas means declining surface pressure. The atmosphere that the New Horizons photographs captured at or near its maximum extent is now shrinking. This decline has already been measured directly. Astronomers monitoring Pluto using the technique of stellar occultation, in which the planet passes in front of a background star, and the dimming and refraction of the star's light reveals the atmospheric pressure, have documented a decrease in Pluto's surface pressure from approximately 1 Pascal in 2015 to roughly 0.91 Pascals by 2020, a reduction of approximately 9% in 5 years. The numbers are small in absolute terms. 1 Pascal of atmospheric pressure is already an almost inconceivably thin envelope of gas. 9% of that is a quantity that would be difficult to measure by any means other than the stellar occultation technique, which is exquisitely sensitive to exactly these kinds of pressure changes. But the direction of the change is unambiguous. The atmosphere is deflating, slowly, measurably, and in a direction that the physics of Pluto's orbital mechanics makes essentially irreversible on any timescale relevant to the current era. The question that planetary scientists have been debating for decades, and that Webb's thermal data now frames with greater specificity than before, is how this deflation proceeds and what Pluto's surface and atmosphere look like at its various stages. The concept involved is called atmospheric collapse, and on Pluto, it refers not to a catastrophic sudden event, but to a gradual transition from a state where volatile ices maintain a measurable gaseous phase above the surface, to a state where they do not. Here is the mechanism by which that transition occurs. As solar energy input declines, the rate of nitrogen sublimation from surface ice falls below the rate at which nitrogen vapor in the atmosphere recondenses onto cold surface regions. More nitrogen is freezing out of the atmosphere than is entering it. The atmospheric inventory of gas diminishes. Pressure drops. As pressure drops, the conditions that sustained haze particle production in the upper atmosphere change. Haze formation requires ultraviolet radiation to drive photochemical reactions involving methane in the upper atmospheric column. As atmospheric pressure declines and the column of gas above the surface thins, the altitude at which ultraviolet photons are absorbed drops. The photochemical production zone shifts. The rate at which new haze particles form decreases. The haze column begins to thin from the top down, losing its uppermost layers first as the gas supporting them drains away. A thinner haze means less radiative cooling, which the Webb data has now confirmed is the primary driver of Pluto's anomalously cold upper atmosphere. Less cooling means the remaining atmospheric gas is slightly warmer. But this warming effect is modest and is overwhelmed by the continued decline in solar energy input as Pluto recedes. The net result is an atmosphere that is simultaneously losing its cooling mechanism and losing its energy source. A system whose two primary processes are both weakening simultaneously in ways that reinforce each other's decline. On the surface, the consequences of declining atmospheric pressure manifest as a gradual reorganization of the volatile ice geography. As sublimation rates fall, the transport of nitrogen from sunlit regions to shadowed cold traps slows. Sputnik Planitia continues to function as a nitrogen accumulation site, but at a diminishing rate. Other regions that previously experienced active volatile transport begin to retain their ice coatings for longer periods, as the sublimation that would normally remove them slows toward insignificance. The surface, which at Pluto's current stage is actively reshuffling its chemical geography in response to seasonal forcing, gradually approaches a more static configuration, not immediately and not uniformly, but directionally and persistently. Methane, being less volatile than nitrogen, persists on the surface through conditions that would cause nitrogen to sublimate away. As the nitrogen cycle weakens, methane's relative contribution to the visible surface composition increases. Regions previously coated in a nitrogen frost layer begin to expose their underlying methane ice as the nitrogen component sublimates away and is not replenished from elsewhere at the same rate. The spectral character of the surface changes. The albedo patterns that New Horizons documented in 2015 are not permanent features. They are a snapshot of one particular configuration in a volatile cycle that continuously evolves. The bright heart-shaped expanse that captured the world's imagination is a temporary arrangement of frozen gas that will look different in a century and may be unrecognizable in several centuries more. The organic tholin material already deposited across Pluto's equatorial regions does not participate in the volatile cycle in any meaningful sense. It is not volatile. It does not sublimate at Pluto's temperatures. It simply accumulates, layer by layer, as haze particles continue to drift down from above. As haze production slows with declining atmospheric pressure, the rate of fresh tholin deposition decreases, but the existing deposits remain. They are a fossil record of atmospheric activity, a chemical sediment that will outlast the atmosphere that produced it by enormous margins. Long after the nitrogen has largely frozen out of the atmospheric column, long after the haze has thinned to the point of imperceptibility, the dark organic staining of the equatorial terrain will remain as a permanent reminder that something once happened here, that an atmosphere once existed above this surface and did chemistry in it, and rained its products down onto the ground below. The most haunting quality of this entire transition is its silence. There is no identifiable moment at which Pluto's atmosphere ceases to exist. There is no event, no threshold crossing, no visible change that marks the transition from a world with an atmosphere to a world without one. The shift occurs in increments too small for any single observation to capture unambiguously. A fraction of a Pascal of pressure lost over the span of years. A slight thinning of the haze column, unmeasurable from one season to the next. A marginal slowing of the volatile cycle that reveals itself only in the comparison of observations separated by decades. The change is real and physical and governed by the same laws of thermodynamics and orbital mechanics that govern everything else in the solar system. But it unfolds on a timescale calibrated to Pluto's own unhurried rhythm, indifferent to the pace at which human scientific careers or human civilizations unfold. Some models suggest the atmosphere could be largely collapsed within a few decades. Others argue that the thermal inertia of the nitrogen ice reservoir in Sputnik Planitia is large enough to sustain sublimation at a detectable level for a century or more, even as Pluto continues to recede. The true answer depends on parameters that remain incompletely constrained even after Webb's observations. The total volume of nitrogen ice available for sublimation in the deep basin, the thermal conductivity of the subsurface layers that determines how quickly the ice responds to changing surface conditions, the feedback effects of the haze itself on the rate of atmospheric cooling as the haze column thins. These are not parameters that Webb's current observations can directly determine. They are questions that will require continued observation over extended periods, combined with sophisticated numerical modeling to answer with confidence. What is not in question is the direction of travel. Pluto's atmosphere is not in a stable state. It reached its maximum extent sometime in the years following the 1989 perihelion, driven by the thermal lag between peak solar heating and peak sublimation response. It has been declining since. The observations confirm the decline. The physics demands that the decline continue. At some point in the future, whether in decades or centuries, an astronomer pointing a telescope toward Pluto will find a world with no detectable atmosphere, a frozen globe sealed under a layer of nitrogen ice, with nothing above it but starlight and the near-perfect vacuum of interplanetary space. The haze that glowed in Webb's mid-infrared data will be gone. The volatile cycle that moves ice from one hemisphere to another will have stopped. The methane leaking across space to Charon's polar regions will have been cut off. The heart-shaped nitrogen plain that became the most famous geographical feature of the outer solar system will still be there, but it will be a static frozen landscape rather than a dynamically active one, accumulating craters over geological time as the impacts that the active surface currently erases resume their slow work. The world captured in the New Horizons photographs, in all its geological and atmospheric complexity, will be a historical record of a temporary state, a portrait of a planet during the brief portion of its long orbit when it was close enough to the Sun for something interesting to happen above and across its surface. That portrait, which the world fell in love with in 2015, may be the only portrait that will ever look like that. The next time Pluto passes through perihelion, 248 years from now, conditions may have shifted enough that the atmosphere reinflates and the volatile cycle resumes. But the specific configuration of surface ices, the exact distribution of bright and dark terrain, the particular thickness of the haze column at that moment may never be precisely reproduced. The Pluto of the New Horizons photographs was a singular version of itself, a configuration shaped by the specific history of where its volatile ices happened to be distributed at that particular point in the late 20th century. That configuration is already changing, and Webb has given us the first detailed thermal portrait of a world in the process of becoming something different from what it has been for the past few centuries. That is the physical reality of Pluto's surface and atmosphere, stripped of the sentimental overlay that popular culture placed over it, not a harmless frozen outcast. A dynamic, chemically active world in the early stages of a climatological transformation that will render it unrecognizable on timescales that are long by human standards, but brief by the standards of planetary science. A world whose most interesting era, at least from the perspective of an observer with instruments capable of seeing it clearly, may already be behind it. And this is only the context immediately surrounding Pluto itself. Step back further, and the picture becomes stranger still. Pluto does not exist in isolation. This is a fact that the popular image of the dwarf planet, with its emphasis on loneliness and exile, consistently obscures. The sentimental narrative requires Pluto to be alone, a solitary outcast drifting through empty space beyond the boundaries of the real solar system, stripped of its title and left to wander in the dark. The physical reality is almost the opposite. Pluto is not alone. It is the largest and most visible member of a vast and populous region of the solar system that extends far beyond Neptune's orbit, and that contains objects numbering in the hundreds of thousands, possibly in the millions, orbiting in a darkness so complete and a cold so extreme that the conditions prevailing there make Pluto's environment seem almost temperate by comparison. This region is called The Kuiper Belt. It extends from approximately 30 astronomical units from the Sun, just inside Neptune's orbit, to roughly 50 astronomical units at its outer edge. Within this volume of space, an estimated 100,000 or more objects, larger than 100 kilometers in diameter, orbit in paths that range from nearly circular to highly elliptical, inclined at various angles relative to the plane in which the major planets travel. Beyond the Kuiper Belt proper lies the scattered disk, a dynamically distinct population of objects with more eccentric and more inclined orbits that extends to distances of several hundred astronomical units. And beyond the scattered disk, if current theoretical models are correct, lies the Oort cloud, a vast spherical shell of icy bodies extending perhaps to 100,000 astronomical units, nearly halfway to the nearest star, containing the source population for the long-period comets that occasionally fall inward through the solar system on orbits lasting millions of years. Everything that most people think of as the solar system, all 8 planets, all their named moons, all the asteroids, all the missions, all the history of human space exploration, is contained within a sphere extending to approximately 30 astronomical units from the Sun. This sphere represents a tiny fraction of the Sun's gravitational domain. If you compressed the entire solar system, from the Sun to the outer edge of the Oort cloud, into the floor plan of a large house, everything that humanity has explored in any detail would fit within the entryway. The rest of the house, room after room extending through corridors that stretch farther than the eye can follow, would represent territory that we have glimpsed at best, characterized in only the broadest terms, and in most cases never observed at all. Pluto sits at the threshold between the entryway and the first corridor. It is the last named world that most people recognize before the darkness begins. And for decades, the assumption that governed scientific thinking about everything beyond that threshold was simple and almost certainly wrong. The assumption was that the outer solar system was dead, that the objects populating the Kuiper Belt and scattered disk were inert, geologically frozen, chemically simple relics of the solar system's formation 4.5 billion years ago, unchanged since the era when the planets were still assembling from the disk of gas and dust that surrounded the young Sun. The assumption was that cold meant inactive, that distance meant irrelevance, that small meant simple. Pluto, examined carefully, had already begun to undermine this assumption before Webb ever observed it. The New Horizons flyby revealed a world of geological complexity, atmospheric activity, and surface chemistry that no inert frozen relic should possess. But New Horizons observed only Pluto. Its trajectory carried it onward into the Kuiper Belt after the flyby, and it did manage a distant observation of a small Kuiper Belt object called Arrokoth in 2019, revealing a contact binary of 2 lobes gently joined in the early solar system. But Arrokoth was one object at close range. The broader population of Kuiper Belt bodies remained largely uncharacterized in any compositional or thermal detail. Webb changed this, not only through its observations of Pluto, but through a systematic survey program called DISCO, short for Discovering the Surface Compositions of Trans-Neptunian Objects. This program, led by a team of planetary scientists using Webb's near-infrared spectrograph instrument, observed dozens of Kuiper Belt objects and centaurs, the latter being icy bodies that have been gravitationally scattered out of the Kuiper Belt into orbits between Jupiter and Neptune, where they are subject to greater solar heating and represent an intermediate stage between pristine outer solar system bodies and active comets. The DISCO survey obtained near-infrared spectra of these objects, with a sensitivity and spectral resolution that no previous instrument could match, extracting compositional information from objects so faint and so distant that even their existence had been uncertain before modern survey telescopes identified them. The results, published in a series of papers in 2025, revealed something that overturned the simple model of the outer solar system as a chemically uniform, frozen wasteland. The trans-Neptunian objects observed by Webb were not all the same. They were not even approximately the same. They fell into distinct compositional groups with significantly different surface chemistries, suggesting different formation locations, different evolutionary histories, and different exposure to the radiation processing and volatile loss mechanisms that have shaped surface compositions over billions of years. One group showed surfaces dominated by complex hydrocarbons and methanol ice, suggesting extensive radiation processing of simpler organic precursors over geological timescales. A second group exhibited surfaces rich in carbon dioxide ice, mixed with lighter organic compounds, a compositional signature consistent with a different initial inventory of volatiles and a different degree of subsequent chemical evolution. A third group showed water ice as a major surface component, mixed with ammonia-bearing species similar to those found on Charon, pointing toward a compositional kinship with Pluto's moon rather than with Pluto itself. The boundaries between these groups were not perfectly sharp, and individual objects showed variations on the general themes, but the overall pattern was clear. The Kuiper Belt is not a population of identical frozen relics. It is a chemically diverse collection of worlds with distinct surface histories, each bearing the marks of processes that operated differently in different parts of the early solar system, and that have continued to modify surface compositions across the billions of years since formation. This chemical diversity extends and amplifies the lesson that Pluto's own examination has provided. Pluto is not an anomaly. It is not a uniquely strange object whose unusual properties set it apart from the rest of the outer solar system in ways that make it scientifically interesting, but broadly irrelevant to understanding the region as a whole. Pluto is the most visible and most thoroughly studied representative of a general phenomenon that appears to be widespread across the entire trans-Neptunian population. These worlds have chemically active surfaces. Their ices are being continuously processed by the radiation environment in which they exist, broken down into simpler fragments and reassembled into more complex compounds by ultraviolet photons and high-energy cosmic rays that reach even the most remote corners of the solar system. Organic material is accumulating on surfaces where temperatures hover at a small fraction above absolute zero, not because there is abundant energy available to drive rapid chemistry, but because even a trickle of radiation sustained for billions of years is sufficient to drive substantial chemical transformation. Consider what this means in physical terms that push against the limits of intuitive comprehension. At 50 astronomical units from the Sun, the solar energy input has dropped to approximately 1/2500th of what Earth receives. The ultraviolet flux, which drives the photochemical reactions responsible for haze production in Pluto's atmosphere and tholin formation on multiple outer solar system surfaces, is correspondingly reduced. And yet, even at this extreme distance, the chemistry continues. More slowly than at Pluto's distance, more slowly still than in the inner solar system, but measurably, persistently, relentlessly, one photon at a time, over timescales that dwarf the entire history of human civilization. The surfaces of Kuiper Belt objects are being chemically transformed. Beyond the solar ultraviolet contribution, cosmic rays, high-energy particles arriving from sources distributed throughout the galaxy, penetrate to the surfaces of Kuiper Belt objects and drive their own form of radiation chemistry. Cosmic rays are far more energetic than ultraviolet photons and penetrate deeper into surface ice layers. Their chemical effects are different from those of ultraviolet radiation, but equally real. Over billions of years of cosmic ray bombardment, surface ices on trans-Neptunian objects are irradiated to depths of meters, with complex organic compounds accumulating throughout the irradiated layer. This is not the productive chemistry of a warm, wet, sunlit world. It is not the kind of chemistry that anyone currently believes leads to life. It is cold, slow, radiation-driven destruction and reconstruction of simple molecules into complex ones, producing an organic residue whose composition reflects the specific radiation environment and initial ice inventory of each individual object rather than any universal template. The named dwarf planets of the outer solar system illustrate the diversity of this phenomenon across objects of different sizes, different orbital histories, and different surface compositions. Eris, orbiting in the scattered disk at distances ranging from approximately 38 to nearly 98 astronomical units, is the most massive known dwarf planet in the solar system, slightly more massive than Pluto, despite being of comparable size. Its surface is bright, one of the most reflective surfaces in the solar system, covered in methane and nitrogen ices that appear freshly deposited, possibly condensed from a temporary atmosphere during Eris's most recent close approach to the Sun. Webb's observations have begun to characterize Eris's surface composition in detail, revealing a world whose surface chemistry shares elements with Pluto's, but whose specific configuration reflects its very different orbital history. Eris spends most of its 559-year orbit at distances where solar energy is negligible, but its periodic close approaches drive bursts of atmospheric activity that may resurface portions of the planet with fresh, volatile deposits before it retreats again into the cold. Make, another recognized dwarf planet orbiting at distances comparable to Pluto's, shows a surface dominated by methane ice with a reddish tint attributed to tholin production driven by radiation processing of surface methane. Its color and compositional signature place it in the same broad category as Pluto in terms of the processes shaping its surface, but its specific properties reflect its own individual history of radiation exposure, volatile redistribution, and thermal evolution. Webb's near-infrared spectroscopy of Make has refined the compositional characterization beyond what previous instruments could achieve, revealing subtleties in the methane ice spectrum that constrain the temperature history of the surface material. Haumea is perhaps the most physically unusual of the recognized dwarf planets. Its rapid rotation, completing one full turn in approximately 3.9 hours, has distorted it into an elongated, ellipsoidal shape that deviates dramatically from the spherical form that gravity imposes on most bodies of comparable mass. This shape is the consequence of a catastrophic collision early in the solar system's history that spun the body up to its current rotation rate and scattered fragments that became Haumea's two known moons. Haumea's surface is dominated by crystalline water ice, a form of water ice that ordinarily reverts to a more disordered, amorphous structure under the radiation bombardment of the outer solar system over geological timescales. The persistence of crystalline water ice on Haumea's surface implies either ongoing resurfacing that continuously exposes fresh crystalline material or some process that prevents radiation damage from accumulating at the expected rate. Webb's observations have contributed to characterizing this puzzle, though the definitive explanation remains an open question. Sedna occupies an orbital regime so extreme that it represents an almost entirely separate category of outer solar system object. Its orbit carries it from approximately 76 astronomical units at its closest approach to more than 900 astronomical units at its farthest, an aphelion distance so enormous that a single orbit requires approximately 11,000 Earth years to complete. At its farthest point, Sedna is so remote from the Sun that solar energy is essentially non-existent, and the only radiation reaching its surface is cosmic rays and the diffuse interstellar radiation field. Whatever chemistry has occurred on Sedna's surface has been driven either by the brief periods of its orbit when solar ultraviolet becomes marginally significant, or by billions of years of cosmic ray bombardment operating at distances where the Sun is indistinguishable from any other star in the sky. Sedna's surface is among the reddest in the solar system, redder even than most Kuiper belt objects, a color consistent with an extreme accumulation of radiation-processed organic material built up over the entire history of the solar system. Webb has not yet obtained detailed spectroscopic characterization of Sedna because of the object's extreme faintness at its current distance of approximately 83 astronomical units, but future observations, as the instrument program matures, may be able to extend compositional characterization to this most remote of the recognized large outer solar system bodies. The picture assembled from Webb's DISCO survey, combined with the detailed thermal and compositional characterization of Pluto itself, fundamentally revises the conception of the outer solar system that the standard mental model of the solar system implies. The region beyond Neptune is not empty. It is not a vacant lot at the edge of a well-ordered neighborhood. It is a chemically active frontier, populated by hundreds of thousands of worlds, each undergoing its own slow transformation driven by processes operating in conditions so extreme that terrestrial analogies barely apply. Every one of these worlds is being modified by radiation. Everyone is losing volatiles to space at rates determined by the balance between solar heating and gravitational binding. Everyone whose surface contains organic precursors is producing complex compounds from those precursors, building up a chemical complexity that has no driver other than time and radiation. Pluto, sitting at the near edge of this population and experiencing the most solar energy of any Kuiper Belt object, represents the most active and most observable version of these processes. Its haze-driven climate, its volatile ice transport cycle, its atmospheric escape and deposition onto Charon, its potential atmospheric collapse, all of these are processes that may occur in attenuated or modified forms on other trans-Neptunian objects, operating under more extreme conditions of cold and darkness. Pluto is the laboratory specimen. It is the case where the processes are fast enough and the object close enough for current instruments to characterize them in meaningful detail. The thousands of other Kuiper Belt objects beyond Pluto's distance are running the same experiments more slowly, in deeper cold, under fainter light, with results that will take decades of continued observation to characterize even partially. What Webb has revealed, both through its Pluto observations and through the DISCO survey, is that the outer solar system is a place of genuine physical and chemical interest that the standard mental model of the solar system completely fails to capture. The mental model ends at Neptune. The physical solar system continues for distances that dwarf the planetary region by factors of thousands, and it is populated throughout by objects whose surfaces are actively evolving in response to the radiation environment they inhabit. This matters not only for understanding our own solar system, but for understanding planetary systems generally. Trans-Neptunian objects and their analogues in other planetary systems, the debris disks that astronomers detect around other stars through infrared emission, represent a universal feature of planetary system architecture. The chemistry occurring on Kuiper Belt objects under the influence of stellar radiation and cosmic ray bombardment may represent a widespread phenomenon in the galaxy, operating wherever icy bodies orbit at sufficient distances from their host stars, that volatile ices remain stable for geological timescales, while radiation processing continues to drive surface chemistry. If Pluto demonstrates that organic haze can dominate a planetary energy balance, and that complex organic compounds can accumulate on surfaces at temperatures near absolute zero, these results provide a framework for interpreting the surfaces of small icy bodies around other stars that future telescopes may eventually be able to characterize. The dwarf planet that most people filed away in the category of cosmic irrelevance turns out to be a case study in processes of genuine astrophysical generality. This is not a coincidence of scale or of location. It is a consequence of looking carefully at something that was previously known only well enough to be dismissed. Better observation reveals depth, where superficial observation found only simplicity. And in the outer solar system, where everything is cold and dark and far away, the temptation toward superficial observation has always been strong. Webb has resisted that temptation. Its thermal and compositional data have transformed the outer solar system from a blank at the edge of the map into a territory with measurable properties, evolving surfaces, and physical processes complex enough to challenge existing models and open new lines of inquiry that will occupy planetary scientists for the next generation. The darkness beyond Neptune is not empty. It is full of worlds that are doing things, slowly, coldly, chemically, on timescales that dwarf human history, but that are no less real for their slowness. And Pluto, the most famous of those worlds, stands at the threshold between the familiar and the genuinely alien, between the solar system that most people carry in their imagination and the solar system that actually exists. Webb has given us the clearest view yet of which side of that threshold the real Pluto occupies. It does not occupy the familiar side. There is a particular kind of discomfort that does not come from encountering something frightening in any conventional sense. It does not arrive with a sudden shock or a dramatic revelation. It settles in gradually, quietly, through the accumulation of detail, as something you thought you understood reveals itself to be something else entirely. The object is still there. The name is still the same, but the more carefully you look, the less the thing in front of you resembles the version you carried in your memory. Until at some point, you are forced to acknowledge that the image you held was never accurate. It was a sketch assembled from insufficient information, populated with projections from your own emotional vocabulary, and mistaken for knowledge because nothing had yet arrived to contradict it. That is what the James Webb Space Telescope has done to Pluto. Not in a single dramatic moment, but in layers, each observation adding detail that pulls the dwarf planet further from the familiar and deeper into a category of physical reality that the sentimental image was never designed to accommodate. The process did not begin with Webb. It has been unfolding for nearly a century, driven by every incremental improvement in humanity's ability to observe this world as it actually is, rather than as imagination populated it. When Clyde Tombaugh found that moving point of light in 1930, Pluto was a name without a face, a designation applied to an unknown quantity that the human mind immediately began to fill with assumptions. It was cold because it was distant. It was small because it was faint. Everything beyond those minimal inferences was projection, and projection, being a human instrument, tends to produce human results. Pluto became an underdog because humans find underdogs sympathetic. It became a cosmic outcast because the narrative of exile and injustice is one that human cultures have rehearsed endlessly across every medium available to them. None of these qualities belong to Pluto. All of them belong to the people imagining it. The Hubble Space Telescope provided the next stage of disenchantment, resolving Pluto as a small disk with blotchy surface markings that hinted at complexity without revealing it. The hints were sufficient to sustain the imagination's license to fill in what the instruments could not see. Pluto remained sufficiently vague to remain whatever people needed it to be. A point of light with a face but no character. A world observed closely enough to confirm that it existed as a differentiated body, but not closely enough to understand what that body actually was. Then, New Horizons arrived, and the image changed with a completeness that nothing in the history of outer solar system exploration had approached. Suddenly, Pluto had mountains and plains, and a heart-shaped feature that the entire world fell in love with simultaneously. It had a blue haze that made it look ethereal. It had geological complexity and surface chemistry and atmospheric structure that transformed it, in the public imagination, from a vague, distant dot into a specific, recognizable world with personality. People printed the heart on clothing. They used the surface photographs as the visual shorthand for wonder and cosmic beauty. Pluto became, paradoxically, more beloved in the years after its demotion from planetary status than it had ever been before. The photographs humanized it, and in humanizing it, they created a new and more detailed version of the sentimental image that was no easier to reconcile with physical reality than the old one had been. Because embedded within those beautiful photographs were details that, examined carefully and honestly, told a story considerably less charming than the surface impression suggested. The heart-shaped feature was not a symbolic gesture from a world that wished humanity well. It was a basin of convecting nitrogen ice, churning in slow geological motion driven by internal heat flux, refreshing its own surface over timescales measured in hundreds of thousands of years. The mountains were not picturesque alpine peaks of the kind that appear on calendars and inspire human aspiration. They were blocks of water ice, so cold that they behaved as structural bedrock, projecting above plains of frozen nitrogen in a landscape where no liquid of any kind had existed at the surface for billions of years. The dark equatorial bands were coated in organic compounds produced by the radiation-driven destruction of atmospheric methane, a slow chemical process, with no analogue in any environment that any living thing has ever inhabited. The blue haze was not a sky, not in any sense that a human being standing beneath it would recognize as sky. It was a column of organic particles suspended in a near vacuum, so thin that the atmosphere supporting it qualified as a hard vacuum by any engineering standard. The blue color visible in the backlit photographs was a scattering artifact, produced only under specific illumination conditions. From the surface, looking upward, the haze would be invisible to the naked eye. The sky above would be black. The stars would be present throughout the local day. The sun would be a cold, bright point without warmth. Nothing about the experience of standing on Pluto's surface would resemble the impression created by those iconic photographs. But the photographs were so visually compelling that most people never looked past the initial impression. They formed an emotional attachment to a version of Pluto that the data did not support, and they carried that attachment forward, without updating it, as the scientific understanding deepened. The heart was a symbol. The blue was beauty. The little world at the edge of the solar system was charming and deserving of sympathy, and that was sufficient. The actual physical composition of the environment, the actual thermal regime, the actual chemical processes operating there, these were details for specialists. They did not penetrate the popular image. Webb completed what New Horizons began by observing Pluto not in the visible wavelengths where surfaces look like landscapes and atmospheres look like skies, but in the mid-infrared, where thermal emission reveals the physical processes that actually govern a world's behavior. Webb stripped away the last layer of visual comfort. In the mid-infrared, there is no heart. There is no blue haze captured in a single iconic photograph. There is a thermal emission spectrum showing surface temperature variations driven by volatile ice migration across a globe whose surface is made of frozen gas. There is an atmospheric signature confirming that organic particles are radiatively cooling the atmosphere through a mechanism found nowhere else in the solar system. There is a chemical transfer of processed atmospheric material across 19,600 kilometers of vacuum to the poles of a neighboring moon, where it is converted into organic tar by ultraviolet radiation. There is a declining atmospheric pressure measurement suggesting that the entire dynamic system captured in those famous photographs may be in the early stages of freezing itself out of existence. This is what the word disturbing means in the context of Pluto's story. Not a monster, not a fabricated threat designed to generate alarm. The disturbance is quieter and in its own way more difficult to process. It is the progressive dissolution of a familiar image under the sustained pressure of better observation. It is the realization that every time humanity has looked at Pluto more carefully, the world has become harder to emotionally accept rather than easier. The closer we look, the less Pluto resembles anything in the mental catalogue of comfortable things, and the more it becomes something cold and strange and genuinely resistant to the kind of understanding that produces reassurance. This represents an unusual relationship between observation and comfort. In most domains of scientific inquiry, better observation makes things more manageable. You study a disease and learn to treat it. You map a genome and understand how an organism functions. You observe a distant galaxy and fit it into a framework of known structures. Knowledge domesticates. Understanding reduces the emotional distance between the observer and the observed. The unknown becomes known, and the known becomes something that can be approached without unease. Pluto reverses this relationship entirely. Every new observation makes it less familiar, not more. The discovery of its geological complexity did not make it feel like a familiar rocky world. It revealed processes operating under conditions that no rocky world experiences. The detection of its haze did not give it a recognizable sky. It revealed a climate driven by organic particles in a mechanism that operates by rules alien to every other atmosphere we have ever characterized. The conformation of volatile transport did not make its surface feel like comprehensible terrain. It revealed a landscape that physically evaporates and reforms in shifting patterns tied to an orbit lasting longer than the entirety of recorded human history. The thermal data from Webb did not bring Pluto into familiar territory. It pushed it further into a regime of physical experience that the human mind was never designed to find intuitive or comfortable. Each finding is individually fascinating. Taken together, they compose a portrait of a world that resists every attempt to render it familiar, that pushes back against every analogy designed to make it accessible, that remains stubbornly and completely itself, regardless of the emotional frameworks that observers bring to the task of understanding it. This resistance is not a quality that Pluto possesses in any intentional sense. It is a consequence of the physical conditions that prevail there, being genuinely outside the range of anything that human intuition evolved to process. We are creatures of a temperate, well-lit, gravitationally comfortable world. The conditions on Pluto's surface fall so far outside the envelope of terrestrial experience that every attempt to bridge the gap eventually runs out of analogy before it reaches the actual numbers. 40 Kelvin, 1 Pascal, 1/1500th of Earth's solar input, a surface made of frozen atmospheric gas, a climate driven by suspended organic particles, an atmosphere in the process of freezing solid. These are not descriptions of a world that human beings were built to find intuitive. They are descriptions of a genuinely alien physical environment, and no amount of sentimental attachment to the name or the photographs changes what the environment actually is. This gap between the cultural image of Pluto and the physical reality of Pluto matters beyond the specific case of one dwarf planet at the edge of the solar system. It reveals something important about how human beings construct mental models of the cosmos and how resistant those models are to revision. The solar system that most people carry in their heads was assembled in childhood, updated sparingly over the following decades, and populated with emotional associations that have nothing to do with the physical properties of the objects involved. In this mental model, the solar system is a well-ordered, well-lit neighborhood where everything has been explored, categorized, and assigned a place in a comprehensible hierarchy. The planets have characters. Mars is red and potentially habitable. Jupiter is stormy and enormous. Saturn has rings that photographs have made familiar. And at the end of the list, small and cold and sympathetic, there is Pluto. Beyond Pluto, in this mental model, there is nothing, empty space. The solar system ends at Neptune's orbit, and the cosmos begins immediately afterward, vast and unknowable, but irrelevant to the specific story of our planetary neighborhood. This model is not merely incomplete, it is structurally wrong in ways that Webb's observations of Pluto and the broader Kuiper belt have now made impossible to honestly maintain. The solar system does not end at Neptune. It extends through the Kuiper belt, through the scattered disk, through the hypothetical Oort cloud, to distances that dwarf the planetary region by factors of thousands. The objects populating these regions are not inert frozen relics. They are chemically active worlds undergoing surface transformations driven by radiation processing and volatile redistribution on timescales that are long by human standards but brief by geological ones. The outer solar system is not a vacant lot. It is a frontier of extraordinary physical and chemical complexity that humanity has barely begun to characterize. Pluto sits at the threshold of that frontier. It is the most familiar representative of a vast and largely unknown population, the best-studied member of a class of objects whose properties are only now becoming accessible to direct measurement. And the lesson of Pluto, seen clearly in Webb's thermal and compositional data, is that the threshold world itself is stranger and more extreme than the popular image ever acknowledged. If the most familiar object at the boundary of the known solar system operates by mechanisms that have no analog anywhere in the inner solar system, what awaits characterization among the thousands of less studied bodies orbiting beyond it? The honest answer is that we do not yet know. We know that they are diverse, because Webb's DISCO survey has confirmed chemical diversity across the trans-Neptunian population that the standard model never predicted. We know that their surfaces are being actively modified by radiation because the spectroscopic signatures of processed organic material appear across the population with a consistency that demands a systematic explanation. We know that some of them may have experienced or may currently sustain transient atmospheric activity, because the volatile ices present on their surfaces are capable of sublimating under the right orbital conditions. Beyond these broad outlines, the details are unknown, and the details, as Pluto has demonstrated so thoroughly, are where the genuine character of a world resides. Pluto is still out there now, at this moment, receding through the outer darkness on the long outbound arc of its 248-year orbit. Its haze particles are still drifting through the near vacuum column above the surface, absorbing the few ultraviolet photons that reach them from a sun, diminishing with every passing year. Its volatile ices are still redistributing slowly across the surface, nitrogen sublimating from sunlit regions and refreezing in shadowed basins, methane persisting on highland ridges where the thermal environment favors its retention. Molecules are still escaping from the upper atmosphere and crossing the gap to Charon's poles, where ultraviolet radiation is still converting them into reddish organic compounds that will outlast the atmosphere that produced them by immense margins. The atmospheric pressure is still declining, fraction by fraction of a Pascal per year, in the direction that the physics of a receding orbit makes inevitable. And the James Webb Space Telescope is still watching. Its mirror still collects infrared photons from a world 5 billion kilometers away. Its detectors, cooled to within degrees of absolute zero, still register the faint thermal signal of a surface whose temperature hovers near the coldest conditions that naturally prevailing environments in our solar system produce. Future observations will add new frames to the time-lapse that Webb's initial measurements began. They will reveal how the thermal map changes as Pluto continues its retreat. They will track the decline of atmospheric pressure and haze column density over years and decades. They will document the redistribution of volatile ices in response to changing illumination geometry. They will watch, in something approaching real time by the standards of planetary geological change, as a world undergoes the transformation from a dynamically active climate system to something colder and stiller and further from anything the human mind instinctively recognizes as a world. None of this constitutes a threat. None of it harbors danger in any conventional sense. There is no monster at the edge of the solar system. There is no ancient hazard waiting to be discovered. There is something considerably more difficult to emotionally process than either of those things. There is physical reality, unmodified by sentiment, unfiltered by the emotional associations that human beings bring to objects they have named and categorized and argued about for generations. There is a world that is genuinely what it is, operating under conditions that are genuinely what they are, regardless of what anyone imagined about it during the century when it was too distant and too faint to be seen clearly. Better observation does not always make things more comfortable. Sometimes it makes them stranger. Sometimes the closer you look, the less familiar the object becomes, and the more you are forced to confront the gap between the universe as it is and the universe as human intuition and human sentiment would prefer it to be. That gap is not a failure of science. It is one of science's most important products. The universe does not owe any observer a landscape that maps comfortably onto prior expectations. It offers what is actually there, in the wavelengths that the instruments can access, at the precision the detectors can achieve, without adjustment for human emotional preference. What is actually there, at the edge of the familiar solar system, drifting through a cold that no human being has ever experienced, and no human body could survive for a fraction of a second, is a world whose atmospheric climate operates by a mechanism unique in all our observations of planetary systems, whose surface is assembled from substances that are invisible gases at any temperature comfortable for life, whose most prominent geographical feature is a basin of convecting frozen nitrogen that will look completely different in a century, whose atmosphere may be in the process of freezing entirely out of existence over the span of a human lifetime, whose molecules escape across interplanetary space and are permanently incorporated into the surface of a companion world as complex organic residue. This is Pluto, not the mascot, not the underdog, not the charming frozen outcast of popular imagination, the real one, the one that the most powerful observatory ever built can finally see clearly enough to describe in physical terms rather than in emotional ones. It is out there right now, cold beyond any terrestrial reference point, dim beyond any familiar experience of distance from a source of light, active in ways that the sentimental image never prepared anyone to consider, changing in directions that will render the configuration captured in those beloved New Horizons photographs a historical artifact within timescales that are brief by any planetary standard. The warmth that most people imagine surrounding that distant bright point has never reached Pluto's surface in any meaningful quantity. It has never warmed the nitrogen ice. It has never penetrated the haze. It has never done more than provide the barest minimum of energy required to keep the volatile cycle turning and the atmosphere from collapsing entirely. And even that minimum is now declining, year by year, as the orbit carries the dwarf planet further from the only source of energy available to it in the outer darkness. What remains is the cold, the chemistry operating within the cold, the instruments sensitive enough to detect it, and the slowly accumulating portrait of a world that becomes more extraordinary the more clearly it is seen, not because it conceals something magnificent, but because the truth of what it actually is, stripped of sentiment and seen in the wavelengths where its thermal reality becomes visible, is stranger and more genuinely alien than a century of imagination ever managed to produce. The universe does not traffic in comfort. It offers reality instead, and Pluto, seen at last through instruments adequate to the task, is one of the coldest, most chemically active, most climatologically singular realities our solar system contains. Not because it is far away, not because it is small, not because it was demoted or exiled or stripped of a title it held for 3/4 of a century, because it is real, and reality, at the edge of the sun's reach, in the wavelengths where heat tells the truth that light conceals, looks nothing like the picture we drew when we could not yet see it clearly enough to know the difference. A single point of light in a black sky, no warmth reaching the surface below, the haze still drifting, the ice still slow churning in the basin, the atmosphere still thinning, molecule by molecule, toward a silence that will outlast everything we have ever built or named or loved on the warm world where we happen to exist. It is out there. It always has been. We simply could not see it until now.